Yeah, but welcome everyone for the role of this week. So I have the pleasure to introduce Francesca Maggioni. She's a professor at the University of Bergamo. She's well known for her research in optimization under uncertainty. Most famous papers for me are papers in stochastic programming and distributional robust optimization. But in total, she published more than 80 scientific articles in peer-reviewed journals. She's the chair of the Euro Working Group on Stochastic Optimization and the AARO thematic section of stochastic programming. And I was very impressed. She's associate editor for a lot of journals, transportation science, computational management science, Eurojournal on computational optimization, and several more. I'm very happy that we have you here today. And please, Francesca.
Thank you very much, Yanis and Reza, for the kind invitation. It's really an honor and pleasure for me to be here and to present these works on the robust seminar series. So I will talk about recent results on sampling and bounding methods for multi-stage robust optimization and distributional robust optimization. These are joint works done in collaboration with great colleagues that I had the pleasure and honor to work in the recent years. So the first part of the talk on robust optimization is based on a work done in collaboration with Fabrizio Dabbene and Professor Georg Flug, respectively from the Polytechnic of Turin and the University of Vienna. While the second part of this presentation is based on another recent work done in collaboration with Professor Guzin Bayraksan of Ohio State University and our two former PhD students, now both researchers in company doing optimization, Daniel Faccini and Arthur Young. More details will come later. So a big thank, of course, to these wonderful colleagues. So I will start now with the main motivation of the topic that I'm going to address. In real words, in several cases, we needed to make a decision which are dynamic and secondly affected by uncertainty. For example, in finance, in production, in transportation, in logistics, energy, pension funds, several are the cases in which we needed to take a decision over time. So this means that they are dynamic, which means that the decision that I make today can be adjusted later, for example, tomorrow or after 1 month, etc. And in between these pairs of decision, some random event will occur. Unfortunately, when we make this decision, we don't know what will be the outcome of these events, and so this means that they are uncertain. So several are the ways, modeling frameworks able to cope with such a kind of difficult decision problems, which I just mentioned here with some nice pictures. So if we don't consider the uncertainty, then we solve a classical deterministic optimization problem. While if we need to solve a problem where we know some information about the probability distribution of our uncertainty, by the way, here the uncertainty is represented by the letter xi. So if we know the probability distribution, then the most suitable approach is the so-called stochastic optimization, where we minimize the expectation over this probability distribution. However, in many cases, we don't have such a kind of detailed information, and so other more robust approaches have been proposed in the literature. Robust optimization, where we wanted to solve, again, an optimization problem, considering all possible realization of our uncertainty xi in an uncertainty set. And in the literature, several types of uncertainty sets have been proposed in order to make the problem tractable, for example, box, ellipsoidal, polyhedral, etc. In between robust and stochastic optimization, more recently, another frame of research, which takes the name of distribution robust optimization, has been proposed. In this case, again, we solve a min-max optimization problem. However, instead of not having information about the uncertainty, so instead of making like an assumption about the support of your uncertainty, we are supposed to have a set of probability distributions. And for example, they belong to a set which takes the name of ambiguity set They can share some information, for example, the moments, or they can be distant with respect to a nominal probability distribution, a certain quantity. And in this case, we wanted to find the best solution in the worst possible realization of the probability distribution in such a kind of ambiguity set. So in this presentation, I will focus on solution methods for the last two modeling approaches, robust optimization in the first part and distribution robust optimization in the second part. However, as I said before, in many real-life problems, the situation that we needed to face are dynamic in the sense that we needed to take a sequence of decision over time. And this means that if we wanted to correctly describe the dynamic decision process, the problem becomes very difficult from a computational point of view. And it can happen that if we wanted to implement the problem on our computer, by increasing the number of stages, our computer can easily go out of memory by solving the full problem, the ideal problem that describes the real-life situation. And so for this reason, approximation techniques, which approximate the problem and provides lower and upper bounds to the optimal value of a multi-stage robust or distribution robust optimization problem, could be very useful in practice. So this will be the main aim of our work. In particular, I will try to answer in this talk the following two questions. The first one is how to approximate multi-stage robust optimization problem via scenario sampling. This approach has been already described in the previous talk by Professor Marco Campi, and so I will base most of the results on that presentation, on a part of the presentation. While the second question that I will try to answer is how to bound multi-stage distribution robust optimization via scenario grouping. So let's start with the first question. So how to approximate multi-stage robust optimization via scenario sampling. So for the sake of presentation, I will just very briefly recall the results which has been provided by Calafiore, Campi, and Garatti, and which refer to static robust optimization problem, where we assume to have a convex function, convex in the decision variable x, where the uncertainty here, again denoted by xi, belong to a certain support capital Xi. So the approach that they propose through the so-called constraint sampling or scenario approach was to, instead of considering the continuum of possible realization of the uncertainty Xi in the support capital Xi, consider a finite number of samples, let's say capital N samples, and then compute in each of these samples the corresponding objective function value. Then their idea is to solve the problem, so the min-max problem, where the max will be done only of this finite number of sample capital N. So for example, here in this figure, which has been inspired by their works, we just extract in this finite support capital Xi 4 scenarios. We compute the corresponding function Z. Here, for the sake of visualization, we just consider the one-dimensional case, but we needed to think also in a higher dimension. And then what we needed to do is to solve, so to find the best solution, x hat, in the worst possible realization over this capital N sample. So, as you can see, the best solution, so the one that minimizes the cost in the worst possible realization that is here represented by this orange line, is here put in x hat with corresponding objective function z hat. However, since this solution obtained just by sampling 4 scenarios is dependent by these 4 scenarios that we sampled, the main question that they try to answer with their results was the following: what happens if we sample now a new scenario, which actually bring a higher cost and if which violate the solution that we obtain just by considering the previous capital N scenarios. So, in other words, suppose that this is the area in our support of Xi, which violate the cost which has been provided by the design obtained by just the capital N scenarios. If we fix a probability of violation epsilon, we wanted to compute an upper bound on this probability of violation of the solution just by considering capital N scenarios. And the main answer to this problem has been provided by this very important and powerful theorem, because as you will see, does not depend by the type of objective function. So the interesting information that we needed to capture is just on the dimension of the space in which the problem is considered. And the theorem says that for any probability level epsilon in 0, 1 and confidence level beta, again in 0, 1, the probability to have a violation larger than epsilon is less or equal than a beta distribution, where you can see that here in the formula appear only the number of samples, capital N, epsilon, that is our probability level given, and small n, where small n is actually the dimension of our decision variable x. So as I said, capital N is the number of samples, and from a practical perspective, what is most interesting to find is this number capital N, because we need to know how many samples we need to extract in order to have a reliable solution. And of course, several are the approaches to find the upper bound to the number capital N. Among them, I would like to mention the one proposed by this paper, by Ramo, Tempo, et al., which says that for any probability level epsilon and confidence level beta, an upper bound on the sample complexity is given by this formula, which, as you see, depends again by epsilon, E, which is the Euler constant, beta, and n, which is again the dimension of our optimization problem. So this is the main reference result that is also the starting point for our research question. So going to the multi-stage framework, so several are the, of course, so the literature addressing multi-stage robust optimization problem is very rich, and we can see that most of the literature here, I just report some of recent literatures, recent papers refer on decision rule approximation plus constraint sampling. So in other words, most of the literature reformulated the multi-stage problem into a static one by rewriting the so-called adjustable decisions, so the decision that we can take at the stage 2, 3, etc., up to the end, as a combination of some basis function of our uncertainty. However, it happened that also by making such a kind of decision rule approximation, the problem can become again still difficult to be solved, and so in the literature, a combination between decision rule approximation plus constraint sampling, being now the problem static, have been proposed. More recently, another approach which has been developed on a specific problem structure is the one proposed by Giorgio et al. In Operation Research 2019, which proposed a robust dual dynamic programming approach. However, this works under special problem structure and like the linearity and uncertainty in the technology matrix or in the right-hand side, and with polyhedral uncertainty. I would like to mention also other papers which refer more to the, oh, sorry, now I think that I lost the presentation. Okay, here. These are more recent papers which has been proposed in the concept of stochastic programming, which apply the same techniques, but as I said, in the context of stochastic programming. So after this brief introduction on related literature, I would like to go step by step, and so build by considering the two-stage case. So in other words, now we consider a problem in which we need to take only two decisions in time, a decision now that we will denote from now on with the letter x1. Then there will be the realization of a random event xi1, and then we can take an adjustable decision x2 after the realization of this random event. For the sake of simplicity, here I just present the linear case. However, the problem can be rewritten also by considering convex objective function and convex constraints. So this is the formulation in which we minimize the first stage cost. And then we need to consider the worst realization of xi1 inside our support capital xi1, where we of a recurse action. Then we have some first stage constraints and other constraints which link first stage and recurse decision. As you see, our decision should be realized for every realization of the uncertainty inside the support capital xi1. We also assume to have a relatively complete recurse. So in this context, we now would like to propose a scenario approach, exactly as has been proposed in the previous paper, as I said, by Calafiore, Campi, and Garatti. So in other words, we now randomly extract a number capital N1 of ID samples of the random variable xi1. And for every random variable, we now introduce, or for any random sample, sorry, we now introduce a second stage variable x2. And so we solve this scenario problem, which is now, as you see, defined over n capital N1 samples, so capital N1 scenarios, and where we have also introduced another decision variable, an epigraphic decision variable, which represent an upper bound of the second stage cost or recurse cost. Of course, since here we are just considering a finite number of possible realization of our random variable or of our uncertainty, this represents an optimistic approximation of our original two-stage robust optimization problem. So this provide a lower bound, and at the same time we have some convergence properties by letting the number of sample go into infinity. So after having introduced the scenario approach, we would like now to try to identify some results on the violation probability of such a kind of approach. So we define, as in the static case, the violation probability as the probability of extracting a new sample such that the cost of the extended problem over capital N1 plus 1 scenarios is larger than the original one. So this is our definition, and the theorem which works for the two-stage case. Here I just report linear case, but of course it works also for the convex case, is that given accuracy level epsilon, the violation probability of a sample-based problem based on a random extraction of capital N1 ID samples of our uncertainty xi1 is bounded as follows. So again, we have the same formula as before. However, we need to add +1, which refer to the epigraphic decision variable gamma that we had to introduce. Small n1 refer to the first stage or non-adjustable decision. So the decision that we need to take at the first stage, and +1, again, as I said, refer to gamma. So in terms of sample complexity, we can see that an upper bound of a number of samples that we needed to extract, given epsilon and beta, is given by this formula where instead of n, we needed to put n1 plus 1. So, I mean, already in the two-stage case, it's very interesting to see the fact that the adjustable decision, so the decision that we needed to take at the second stage, does not make they don't play any role in such a kind of probabilistic result. So now, after the two-stage case, let's see what happened if we go in the more general case, where we needed to take a sequence of decision over capital H plus 1 stages. So in other words, we are in the multi-stage case. And the nested formulation of a multi-stage, robust, convex optimization problem where the objective function is expressed as a nested objective function where C are the function, the cost function at each stage. Here we assume that they are convex in the decision variable x and continuous in both x and uncertainty psi. And here I report, on the other hand, linear constraints, again for the sake of simplicity, also because of the convergence results that we obtain are based on the assumption that the constraints are linear. So we can see that we have some first stage constraints and then some constraints linking the decision variable between one stage and the next one. And as you see, the uncertainty appear over time. So Xi1 will represent the uncertainty in the first period up to capital Xi capital H, which appear in the last period. So in other words, the aim of this problem is to find a sequence of decision variable. The process is non-anticipative, and with xit, we represent the uncertainty defined on capital Xit, while with xi up xt, we denote the history of the uncertainty up to time t. Again, Ct is convex, and we assume relatively complete recourse. From here, so this would be our problem that we would like to solve or approximate. We apply the same techniques as before. However, since we are in a multi-stage setting, we have now, as we have seen, a collection of uncertainty set over time. So what we do is to consider a collection of independently sample value for each of the uncertainty sets over time. So this will be in the first period, this will be in the second period, up to the last period, which can be organized in the form of a scenario tree. So in other words, suppose, for example, to have a three-stage problem. Here is the first stage decision or non-adjustable decision. We extract or we sample capital N1 scenarios. Then we can make a second stage or adjustable decision, which will be done for all the capital N1 scenarios that we have sampled in the first period. And then for each of these realization and for each of these decision, we what we can do is again to sample another number, capital N2 of scenario from the second uncertainty set, capital Xi2, and so take a third stage decision. For the sake of visualization, I will show you later how the scenario tree can be organized and how the uncertainty can be described in a multi-stage case. So after constructing such a kind of scenario tree, I will now pass to the finite problem on the sample tree. So in other words, as have been done for the two-stage case, we substitute the sup with the max. So in other words, we now consider the worst realization over the finite number of scenarios that have been sampled in each of the period, and we solve this sample problem where you see that all the constraints are repeated just for the number of samples that are considered in each of the period. Again, also as in the multistage case, this represents an optimistic approximation of the original multistage robust optimization problem because we sample a finite number of samples, so a subset of the possible realization of our uncertainty. So this represents lower bounds to the optimal objective function value. However, under suitable conditions that I don't mention here because they are quite technical, but I refer to the paper later in the references for details. Again, convergence results hold true, letting the number of samples in each of the period go into infinity. So let's now pass to the most important concept or the new concept that we had to introduce in the multi-stage setting. So as there was in the static case the definition of a violation probability, now we need to introduce a violation probability which depends by the stage in which it happened. In particular, we introduce the violation probability at stage t as the probability to sample at stage t a new sample, such that the objective function of the extended scenario tree, where we add just at the stage t the new sample, is larger than the objective function of the original scenario tree. For the sake of visualization, let's now summarize it with this figure. Suppose to consider a three-stage problem where we have the uncertainty in the first period, capital Xi1, here represented in the y-axis, while the uncertainty in the second period, capital Xi2, in the x-axis. Again, for the sake of visualization, I will just suppose that they are one-dimensional in each period. However, you can think also to generalize to higher dimension. Suppose that we sample three scenarios in the first period, given by 0,2, 0,8, and 0,6. And in the second period, we extract two scenarios with values 0,3 and 0,8. So after such a kind of extraction, we obtain a scenario tree where, as you see, we put together all the scenario in each period. Okay, so we assume that they are independent, and so we need to make the Cartesian products of all the possible realizations. So, for example, for 0,8, I have in the second period the realization 0,3 and 0,8, and similarly for all the others. So in total, I have 6 scenarios which correspond to these 6 points in the square. So the violation that will occur in the first period will correspond to a new extended scenario tree, which correspond to the one where I have sampled a new scenario in the first period. For example, the value is 0.4, such that the extended scenario tree has an objective function which is larger than the one before. So you can see that by extracting a new sample, 0,4, we needed to add a subtree because we need to take into account that also in the next period, the randomness will occur. So in other words, this new extended scenario tree will have now 4 scenarios in the first period and 2 in each of the second period, condition, of course, to the history. So this will be the violation at stage 1, while we say that we have a violation at stage 2 in a similar way, while instead of extracting a new scenario in the first period, we needed to extract a new scenario in the second period. So, for example, suppose that in the second period we extract now scenario 0.5, and so this means that the new extended scenario tree will be now occur like this, where we put or we add the scenario 0.5 for each of the 3 realizations of the scenarios that occur in the previous period. Again, for the sake of visualization, this has been done just for the 3-stage case, but you can think in a similar way a definition of a violation probability in a higher number of stages. I would like to also address the fact that the approach that we have used, which use scenario 3, is different with respect to one done in the literature, where decision rules allow to make decision and describe the uncertainty over path, while we have uncertainty on such a kind of structure. So, for example, here on the left, we can see that the uncertainty has been considered in the first period, and then thanks to the decision rule approximation, we consider just one single path, while through the proposal approach that I just presented, we consider a full scenario 3. So the number of realization of the uncertainty are typically larger. So after this, then we are ready to provide the theorem which provides the violation probability at stage T of the sample scenario 3, which is the following. So given an accuracy level epsilon in 0, 1, and defining n bar t minus 1, the product of a number of sample up to time t minus 1, and defining epsilon t, the ratio between epsilon and this n bar t minus 1, then the probability of a violation at stage T is less or equal than the product between n bar t minus 1 and beta, where this depends by the number of sample of time t, epsilon t, and the number of decision variable at stage T plus 1. Of course, I don't have time to enter into the proof of this result. However, I would like to say that this is mainly based on a variable split notation on the scenario 3 and on this lemma, which is valid for a sequence of identically distributed but possible dependent random variables. So we have used this kind of well-known result in order to obtain an upper bound on the probability of violation at stage T for the scenario sample 3 approach. So let's now see practically how is the sample complexity by applying the previous approximation of a sample complexity that I mentioned in the static case, and by adapting it to the new formula that we derived for a multi-stage case. So the number of samples in the first period has to be chosen larger than this quantity, where you see it appears the dimension of a decision variable in the first period plus 1, which again refer to the epigraphic decision variable. Then given this number, the number of the sample that we should take at the second period should be at least given by this number, etc. So in general, the number of sample at time t should be at least equal to this number. So a simple example, suppose for example to choose epsilon given by this number and beta given by this number. You can see that the corresponding number of sample in the first in the second period as this behavior. So you can see that the main problem appear for the number of sample that we require at later stages. Of course, here we did not make any assumption of a problem. We just have an assumption on the convexity of the problem. We don't have any assumption on how the uncertainty set is done. So we can have any form of uncertainty set. It can be ellipsoidal, polyhedral, box, or it can have the shape that we like. And so these are quite, conservative results, which represent on an upper bound of the number of samples that we required. We can, from a theoretical perspective, also define the total violation probability, because before we define the violation probability at each single stage, so we can define also the probability, which is total, which says that we needed to have at least one stage such that the cost of the extended scenario tree is larger than the original one. And of course, the total violation probability has an upper bound, the sum of the violation probability occurring in each of the stages. So then what we did was also to present some or to propose some approximation which are not based on a sample version, but by relaxing some of the constraints on the information on the uncertainty and the one lower bound that we propose is the so-called robust wait and see, which is just like a reformulation of the so-called wait and see approach, well known in stochastic programming. So in the robust wait and see, we can relax the non-anticipativity constraints and take the soup outside of the problem. So instead of having a nested formulation as seen before, we can then take the soup outside. So in other words, we already know at the beginning what will be the sequence of uncertainty over all the stages. And so this kind of definition allow to define the so-called robust value of perfect information, which is given by the difference between the objective function value of the original robust optimization problem with respect to the objective function value of this kind of relaxation. In a similar way, instead of relaxing the non-anticipativity constraints for all the stages, we can just relax for some of the periods. And in this way, we can obtain a chain of lower bounds. So, for example, if we leave the uncertainty in the first period, but we relax in the next stages, we can obtain like a robust two-stage relaxation. Then if we go one step further, three-stage relaxation and so on. So in other words, what we can obtain is a monotonic chain of lower bound, which approximate from below the objective function value of the original robust optimization problem. And then we can also propose a chain of sample-based lower bounds, which has been obtained by making a sampling of the lower bounds. So of course, this kind of lower bounds is weaker than the one based just on relaxing the non-anticipativity constraints. However, it could be that some of these problems are still hard to be solved, and so you need a sample version to approach them. I would like now to present some numerical results. The first numerical results is based on an inventory management with cumulative orders. So this is the model. I don't enter into the detail of it. This is based on this on an application which was proposed in the paper by Janos, Kuhn, and Rumster. And so here there are the results. Here there are the results, first of all, for the two-stage case and then to the multi-stage case. So first of all, we compute the optimality gap given by the difference between the objective function value of the sample version minus the original one divided by the original one. Here, in this case, we were able to solve the original robust optimization problem as benchmark. And so we can see that for different values of epsilon, from 30% to 0.05, the optimality gap reduce and go into zero. Here we can see, on the other hand, the empirical violation probability of the sample-based approach. We can see again that as epsilon decreases, the violation probability converges to zero, and the empirical violation probability is less or equal than epsilon in all the cases. So, for example, here the maximum value is 17, while epsilon was supposed to be 30, etc. And here there are some results in terms of mean solver time, represented with that dotted line, and the continuous line, on the other hand, represent the sample complexity. So in other words, the minimum number of samples that we have considered for obtaining such a kind of results. On the other hand, for the multi-stage case, what we did was to compute the optimality gap for a three-stage case of the aforementioned problem. We can see that in this case, due to the large number of samples required for later stages, we just consider 30% and 30 and 20% values of epsilon. However, we can see that the optimality gaps are very little, with the worst value equal to 0.08. On the other hand, these graphics refer to the results of empirical violation probability. The empirical violation probability has been obtained by considering 1,000 new scenario trees, which has been obtained by extending or adding one scenario in each stage. So, for example, in the case t is equal to 1, we just add one scenario in the first period, and then we count the number of times the objective function value is larger than the original one, and we make an average over 1,000, and then we compute the statistics over 100 cases. This graphic refers to the first stage violation probability, while this one refers to the second stage violation probability obtained by applying the previous theorem. We can see that in general, the violation probability is larger in previous stages, while in the second stage is very low. And this is a general trend that we have observed. Finally, we would like to also present some results for the two-stage relaxation and the wait-and-see relaxation. So in other words, these are results based on relaxing the non-anticipativity constraints. We can see that these types of lower bounds are very weak because the wait-and-see brings an optimality gap of 68%, while the two-stage relaxation of an optimality gap of minus 39%. And so by applying the sampling techniques on the two-stage relaxation brings optimality gap that are quite far away from the optimal value. On the other hand, in terms of violation probability, the two-stage relaxation provides good results for the first stage decision, because you can see that, again, we obtain a violation probability that is less than epsilon for all the cases. However, very interestingly, the violation probability at stage number 2 is all the time equal to 1, independently of the value of epsilon, showing that such a kind of relaxation is good for approximating solution in the first period, but not in later stages. Secondly, we also consider a case in which the objective function was a convex objective function. This also to show that our approach is general. And I mean, it can be applied to any type of convex optimization problem. So we modify in the previous model the objective function in order to include some quadratic terms, and we obtain similar results for the empirical violation probability and optimality gap as in the linear case. Again, we obtain a larger empirical violation probability in first stage compared to the second one. So this concludes the first part of the talk, which refers to robust optimization. Now I would like briefly to also mention other techniques completely different to the previous one, which refer to provide bounds based on the idea of scenario grouping for multi-stage distribution robust optimization. So the problems that we are going to consider are the following type. So we have the same structure as before, but instead of considering the worst possible realization of the uncertainty inside a certain uncertainty set, we now consider some probability distribution which belong to so-called ambiguity sets. So we have actually these sets which depends by the history up to that time. So they are called conditional ambiguity sets. And in such a kind of description, again, X represents the decision variable, Xit, the random variable defined on the support Xit filtration, and we have having some nominal probability distribution Qt, while Xit with apex t represents the history of the process up to time t. These conditional ambiguity sets, which represent the set of possible probability distribution, can be described in a general way as the set of probabilities having a distance with respect to the nominal one less or equal than a radius rho t of uncertainty or ambiguity. For example, just for a visual representation, we can see here our nominal probability distribution at time t and a class of probability having a distance less or equal than rho t. We needed to think to apply such a kind of conditional ambiguity sets in a multi-stage setting. And so in other words, we are like constructing in each stage some ambiguity which depends by the history which to arrive to that kind of uncertainty. Several are, of course, the approaches which has been proposed in the literature to construct ambiguity sets. Very broadly, we can describe as moment-based, probability-based, or phi divergences. In particular, I will just now mention results based on Wasserstein matrix and phi divergence matrix. In terms of bounds for distribution robust optimization, the only paper available to the best of our knowledge is the one appearing in journal, Info Journal of Computing. So very briefly, what we mean for phi divergence and Wasserstein distance. The phi divergence is one way that we can use in order to construct such a kind of ambiguity set, and this is defined according to this formula, where Q represents our nominal probability distribution on a finite number of realization or scenario, while P is a generic probability distribution. We assume that the phi is a convex function, and when P is equal to 1, this function phi is equal to 0, which means that the distance between the two is equal to 0, and we also have these limit properties. Several are the phi divergences, of course, available in the literature. Just to mention a few: variation distance, Cressy-Red, J divergence, chi divergence, etc. On the other hand, the Wasserstein distance is another way that we can use in order to construct ambiguity set, and this is obtained by solving the following transportation problem, which allow us to decide how much to transport from one probability distribution to the other one, where again Q is the nominal one and while P is another one, generic. So the idea that we have used in order to construct bounds for distribution robust optimization problem is based on an idea that we have used in the stochastic programming setting, which is based on dividing the support of the uncertainty into some subproblems, which are simpler to solve than the original one, and then combine the objective function value in order to obtain a lower bound to the original one. So in other words, suppose that capital Xi is our original support of the uncertainty and Q is our nominal probability distribution. The idea is to split into some independent problems or subproblems. They can be disjoint or they can also share some reference scenarios. And also split the corresponding nominal probability distribution into some probability distribution defined in each of these subproblems, where Pg represents the weight of each of these subgroups. Let's keep in mind this Pg because it will be relevant for future. So we have proposed two approaches to provide lower bounds. The first one, that we call first level criteria, is the following. So we start with a scenario tree. The idea is to split into some subtrees, for example, just composed by two scenarios. We solve each of them as a DRO problem. And so in other words, we needed to fix some ambiguity or level ambiguity in each period, row 1, row 2, and accordingly also in each of these subproblems. We obtain the objective function of these subproblems, and then we needed to combine this objective function value of the four subproblems again in a DRO way. In other words, we fix rho bar as a radius of ambiguity, which is centered on the probability that we denoted before by this pi g. So pi g are the weight of each of the subgroups. And so, in other words, to obtain a lower bound to the original DRO problem, we needed to solve two types of DRO problem. First of all, by solving each of the subgroups DRO problem and then merging them, keeping as a nominal probability distribution the weight that we gave before in the nominal probability distribution. So this provides the first level criteria. while we also propose a second level or multi-level criteria where we combine the subproblem in a nested way. For example, the first with the second one, and then the third with the last one, and then again combine the two problems that we obtain by a new radius of ambiguity to obtain a lower bound to the original problem. So in other words, instead of combining all the subproblems, we combine them following the structure of the original problem. I will not enter into the detail. So how to ensure that we obtain a lower bound to the original one? Of course, it depends by the measure of distance that we've used, phi divergence or Wasserstein, but also by the choice of the parameters, rho bar and rho bar bar, with respect to the original ready rho t. And the answer that we gave are provided by these two theorems. The theorem number one refers to the first level criteria, and this works true only for phi divergences. So suppose that we have a Diaro problem, we describe the ambiguity through phi divergences with the risk parameter rho1, rho2, rho capital H. Then we partition our uncertainty support into some subgroups according to the procedure that just described before. Then if we consider rho bar max the maximum of the ready among all the groups considered, if we satisfy this kind of relation according to the phi divergence that we consider, variation distance, J divergence, etc. So this means, for example, for variation distance, that the ready should be less or equal than rho1, where rho1 is the radius of the original Diaro problem, just in the first period. Then this is a sufficient condition to obtain a lower bound to the original Diaro problem. Similarly, for the other multi-level bounding criteria, we have also obtained some sufficient condition to obtain lower bounds. This holds true for phi divergences, but also for Wasserstein distance. And here are the sufficient conditions. So the interesting part is that if we choose the rho bar and rho bar bar with respect to the original ready, satisfying the corresponding relation, then for sure we have a lower bound to the original Diaro problem. Then we briefly, I will do just in a few minutes, a couple of minutes, present some numerical results on a multi-stage mixed integer production problem. This is the risk-neutral formulation. We have considered a 6-stage scenario tree and the level of robustness equal to 0.5. We include several types of phi divergences. For example, for the modified chi-square distance, we reformulate the problem as follows. And here there are the results. The first line refers to the first level, while the second line refers to the multi-level lower bounds for different combination of rho bar bar and rho bar max, and for increasing cardinalities of the scenarios included in each subgroup. What we can see is that in general, when we have a very small scenario subproblems, for example, here L equal to 1, it makes more sense to put more weight to rho bar bar, because you can see, for example, here we have a lower bound that it is around minus 1,845, for example, and here it passes to minus 1,700. Obtained with the same dimension of the subgroups just by changing the cardinal, just by changing the ready rho bar bar. So here it was equal to 0, while here is equal to 0.50. And similar results are also obtained for the multi-level lower bound. Of course, we can obtain other results with Wasserstein distance. In this case, we could apply only the multi-level lower bound. So in other words, the second theorem that I presented, and again, similar types of lower bounds for different combination of rho bar bar and rho bar max have been obtained. Again, similar trend can be described. So the concluding observation are that the greater the number of scenarios per subproblem, the sharper is the obtained lower bound. As the cardinality of the scenario in each subgroup decrease, more importance should be assigned to rho bar bar at the expenses of rho bar max. And when we consider just a single scenarios, a problem, the best lower bound is obtained by putting rho bar max equal to 0 and rho bar bar equal to rho. In general, we have obtained that for the section with smaller cardinality, the multi-level criteria appear to be more effective than the first level, while the opposite for larger cardinality. The first level appear to be more effective than the multi-level criteria. So in conclusion, in this talk, I've presented two different approaches to cope with multi-stage optimization problem under uncertainty. In particular, a focus on multi-stage robust optimization and multi-stage distributionally robust optimization. In the robust optimization setting, we have obtained probabilistic guarantee for constraint sampling. The main advantage of a proposed approach is that it's very general, avoid parameterization through decision rule, does not make any assumption on the shape of the uncertainty set. Of course, better results could be obtained by exploiting special problem structure of the considered problem. On the other hand, in the DRO context, the bounds are based on a scenario tree decomposition via group subproblems, and we have obtained two theorems providing condition to ensure lower bounds on the risk parameter. The advantage also of the second approach is that it is very general and does not make any assumption also about the integrality of the decision variable. So it also works for two-stage, multi-stage, with also integer decision variable. And here are a selected list of references. The two works that I presented are the first one and the number 6, while all the other ones have been very important and inspiring for our research. I would like to thank you for listening me here, and I would like also to thank the project on which both of the works have been supported. Thanks.